All right, let's jump straight into this explainer and look at the hidden physics that governs some of the most jaw-dropping stunts on Earth. We've all seen these breathtaking acrobatic feats that just seem to defy gravity, right? But the secret to these seemingly impossible acts isn't magic, and it honestly isn't even just raw athletic strength. It's actually a fundamental principle of physics that dictates exactly how every single object in the universe spins. Picture this. You step out onto a high wire 150 meters in the air, and there is absolutely nothing but a terrifying drop right below you. If you've seen daredevils like Nick Wallenda do this, you've probably noticed they almost always carry a ridiculously long, heavy pole. And honestly, it looks so cumbersome, almost like it would make balancing way harder. But today, we're going to uncover exactly why carrying that massive, heavy pole is the one thing saving the performer's life. To get a feel for this, try a quick mental experiment with me right now. Hold your finger out and imagine balancing a long 1 meter ruler upright on the very tip of it. Got it? Okay, now imagine trying to balance a tiny 10 centimeter ruler the exact same way. You instinctively know the longer one is easier to balance, right? It falls over a lot more slowly, which gives your brain and your hand far more time to react and correct those little wobbles. The shorter ruler just zips out of control before you can even process what's happening. So this brings us to section 1, defining moment of inertia, or the rotational analog to mass. Both the tightrope walker and that long ruler are basically exploiting this exact physical property. Think of it as a brilliant, invisible shield against spinning. Now, think about regular linear momentum first. You know that any mass has a natural resistance to changing its velocity when you push it. That's just standard inertia. I mean, it's a lot harder to push a boulder than a pebble, right? Well, the moment of inertia is simply the rotational version of that. It is an object's built-in resistance to being spun, or if it's already spinning, its resistance to being stopped. So the larger this moment of inertia is, the more torque, or rotational force, you're going to need to alter its rotation. And here's where it gets really cool. Looking at the formula I equals mr squared, we have a point mass, which is the m, rotating around an axis at a distance of r. What this perfectly captures is that your resistance to spin depends on your mass, sure, but it depends incredibly heavily on how far away that mass is distributed from your axis of rotation. Because that r value is squared, doubling your distance from the center actually gives you 4 times the rotational resistance. So, bringing this right back to our daredevil out on the wire. By holding that long pole, the tightrope walker is taking mass and pushing it incredibly far away from their body center line. That r value just skyrockets. This drastically increases their total moment of inertia, and as a result, the time it takes for any small wobble to happen is increased. They're buying themselves precious extra seconds to correct a potentially fatal sway. They are quite literally manipulating physics to slow down time. Let's move on to section 2, the bike wheel experiment and how we actually measure inertia in the lab. Because, you can't exactly drop a spinning wheel on a standard bathroom scale to see how much it resists spinning. It turns out you can measure it with just some basic string, a weight, and a simple bicycle wheel. To find the wheel's unique inertia, we run a really precise sequence. First, we attach a known hanging mass to a string, wrap it around the edge of a frictionless bike wheel, and just let it drop. Gravity pulls the mass down, creating tension in the string, and that tension applies a torque right to the edge of the wheel, forcing it to angularly accelerate. By measuring exactly how fast that mass falls, we can completely reverse engineer the wheel's resistance to spinning. This setup brilliantly illustrates the rotational equivalent of Newton's second law. You probably remember force equals mass times acceleration, while over in rotational land, torque equals moment of inertia times angular acceleration. The downward force of tension on this wheel acts at a perfect 90-degree angle to the radius, and that creates pure rotational torque. So if we know the torque and we measure the acceleration, boom, the moment of inertia is revealed. Up next is section 3, conserving your angular momentum, which is basically the figure skater's secret. Let's look at how elite athletes manipulate these equations in real time. We have all watched an Olympic ice skater go into a spin. They always start out slow with their arms and legs extended wide. Then they pull their arms in super tight, and suddenly they turn into a human blur. When they stretch back out again, they slow right back down. This is the law of conservation of angular momentum in action. It's a fundamental law stating that if no outside torque is acting on you, your total rotational oomph, your angular momentum, has to stay perfectly constant. Since that total momentum is completely conserved, it creates this fascinating seesaw effect between your inertia and your speed. Just take a look at a diver going from a wide pike to a tight tuck. The second they leave that diving board, there's no more torque pushing them, their total momentum is totally locked in. So, if they pull their mass tightly inward to drop their moment of inertia, their angular velocity absolutely has to skyrocket to compensate for it. They're trading their inertia for speed. Then, when they open back up to hit the water, they increase their inertia, which slams the brakes on their spin so they can get a clean entry. And listen, this isn't just some party trick isolated to professional sports. This exact conservation of momentum governs our whole reality. If you have ever been on a playground roundabout as a kid and crawled toward the center, you absolutely felt the whole thing mysteriously speed up. It's the same reason a yo-yo accelerates. It is even why planets traveling in elliptical orbits physically speed up as they get closer to their star. The mass gets closer to the center, the inertia drops, and the speed shoots up to keep the universe's ledger perfectly balanced. Which leads us into section 4, flywheels and future energy. How exactly does this resistance to spin solve modern engineering problems? Well, it turns out we can use the moment of inertia to build a totally different kind of battery. Enter the flywheel. Engineers are using these heavy metal discs with massive moments of inertia to literally store energy. Instead of chemical batteries like the lithium ones in your phone, a flywheel is a mechanical battery. You use input energy, say excess electricity from a solar farm, to spin up this giant disc. Because it has such a huge moment of inertia, it takes a serious amount of torque to get it going. But once it is spinning, it stores all of that effort as massive amounts of rotational kinetic energy, just sitting there waiting to be tapped into whenever the power grid needs a boost. To build the ultimate version of this mechanical battery, engineers have to optimize a few key factors. Increasing the overall mass definitely helps, but remember our formula, I equals mr squared? Pushing that mass out to the edges is way better. That is exactly why high-tech flywheels so often have these spoked shapes, hoarding almost all their mass at the absolute outer rim to maximize that r-squared value. They also spin them inside completely sealed vacuums, sometimes even levitating them with superconductors, just to eliminate any friction. They are trapping as much energy as physically possible inside a frictionless spin. As we wrap up this explainer, I want to leave you with something to chew on. From the life-saving balancing pull of a high-wire walker to the blinding spins of an Olympic skater, all the way up to massive futuristic batteries floating on magnetic fields, it really all comes down to controlling exactly where mass lives relative to an axis. So armed with the power to completely control your own resistance to spin, what physics-defying stunts would you suddenly be capable of? Keep that in mind the next time you watch a diver flip, or just spin around in your office chair. Thanks so much for learning with me today.